This is the first video on Introduction to Magnetic Fields. It's fairly basic. A lot of the stuff you should already know, but it's something that you need to just run through just to make sure you've got everything in place in order to carry on in the module. We're going to look at what are the basic laws for forces between magnetic poles, what we mean by a magnetic field, and how can we describe, draw and measure magnetic fields. So first up, the basics. What is the difference between a magnetic material and a magnet? You should know that there's only iron, nickel and cobalt that are actually magnetic materials, and these, if you want to stick something to a magnet, then that thing that you're sticking to a magnet has got to be made of, or part made of, one of those three, and the magnet itself has to be made from one of those three. The difference between a magnetic material and a magnet is to do with how all the domains within the material have actually been aligned. What's behind the magnetism is very complicated, way beyond Gear 13, and it's to do with the spin of the electrons, the quantum spin of the electrons, and the orbits of the electrons, and whether there's complete shells. But you can align all of these properties to make a magnetic material into a magnet. How might you magnetise and demagnetise a bar of steel? Well, one way you can do this, you might have seen it in lower school, is by rubbing a magnet along the steel, and this does actually align some of these domains. How might you investigate the magnetic field around a magnet? Plotting compasses are quite useful, you might have done in lesson, and also the good old iron filings through a salt shaker allow you to see a magnetic field, which we'll look at. What forces act in each of the previous cases? You need to know that opposites will attract and same poles will repel. Fairly basic stuff. And how is a stronger magnetic field represented with field lines? This links in with our study on electric fields, where the closer the field lines are, the stronger the magnetic field is. Okay, you may have seen this. If you had these two magnets, a north and a south, these are obviously going to attract, and a north will repel. But to show this, we would put in field lines. These are our field lines. You can see that the field lines are going between the poles of the magnet from the north to the south, and they're heading back round. If you can see, these field lines will come back round to a south pole. Just as here the field lines have gone from north to a south, then these field lines here are going to be heading back round to the other end of the bar magnet. So the field lines always start at a north pole and end up on a south pole. It's important you know these two diagrams and possibly other ones as well as we go through the course. So some definitions here. A magnet has a magnetic field around it, shown by field lines. We often call these lines of flux. The direction of field is shown by the direction of a force that a north pole would experience. Lines of flux always go from north to south. If we just go back to the previous, if you put a north pole, then a north pole is going to be repelled from this north pole, hence the arrow is pointing away from the north pole. The density of field lines gives you an indication of the strength of the field, and we measure this with the quantity magnetic flux density with the symbol B, and this is the strength of the field, and it is a vector because it's going to have direction. Magnetic flux density, the units, is the Tesla, capital T, and this is the force per unit length per unit current on a current carrying conductor at right angles to a field. But this is basically the force between two wires that are carrying a electric current. Some typical values: the Earth's field has got a magnetic flux density of around 50 microteslas. Obviously it varies dependent on where you are on the Earth's surface. A typical bar magnet that you'd use in the lab, about 0.1 Tesla, and a fridge magnet you've got at home maybe about 0.05 Tesla. So you can see you don't very often come across magnetic fields that are more than 1 Tesla or something like that. Your typical bar magnet is about all you get normally in the lab. Okay, flux patterns around a current carrying conductor. The definition of the Tesla we've just mentioned is to do with the force between two wires. This is because if you allow electricity to flow through a wire, then you get a magnetic field around it. We'll look more into this in the next few lessons. This is the shape of the magnetic field. It's a circular field. You can see here it's been done with iron filings. There's a way of remembering the direction of the field, and it's to do with, it's called the right-handed screw rule. If you imagine you've got a screw being screwed in, to screw this screw inwards, so as the screw moves down you'd have to turn it towards the right, yeah, so to turn it towards the right the screw would go down. So if the current's flowing down, the magnetic field goes around to the right. If you put a wire and you bend it in a sort of coil shape, you can see here this is a wire going up through a piece of paper around a coil, then you would see that the two circular fields begin to interact, and you end up with sort of what almost is nearly getting close to a bar magnet, where you've got the field lines going sort of here from the north heading back round to the south. And if you extend this a little bit further and you keep coiling the wire up into what we call a solenoid, this is a solenoid where you've got a coil of wire, then the effect really does get exaggerated, and you do end up with pretty much what's like a bar magnet. And you can remember which end is the north pole by looking at the direction of the current at each end. If you look at the end of here, then if you imagine the end of this is going to be anti-clockwise. If you imagine the current flowing around that coil, it's going in an anti-clockwise direction, which means this is the north end and this is the south end. And if you did the experiment with the iron filings, you can see this is showing you the field lines quite clearly here, that this is acting in the same way that a bar magnet would.